Well, good afternoon. Welcome back. So in this morning's first MFCS lecture, I introduced you to what is called propositional logic, some of the key points. At the moment, there are only two kinds of values, true and false. The various kind of operators over those values. We can build up formulae. Sometimes those formulae may look rather different, yet turn out to be, key idea, logically equivalent. And then we also saw in the lecture that there are algebraic laws over these operators. Particularly, they come out nicely because we have chosen to take and inclusive or, which nicely mirror each other. So in this second lecture of the day, the title, you can see, is teasingly ambiguous. Am I saying, well, you might have thought this morning's operators were logical, but these ones are going to be even more logical? No, I don't mean that. I mean, well, we've seen some logical connectives. We need to talk about one or two more. More. That's a bit vague. How many, I wonder? So we'll start there. A little theorem. Here it is. Let's just take that much at the moment. So here's a little theorem. There are, no, this is not a typo. Okay. There are 2 raised to the power 2 to the n, logically distinct, i.e. no two of them are equivalent, logically distinct propositions over n different variables. So you might wonder, how many different things can we say? You know, if we've got 3 variables, 4 variables, 5 variables that are logically inputs, how many different possible states of affairs can we capture in a logical formula? And there is your answer. I'll come to you in just a moment. 2 raised to the power 2 to the n if we have n variables. Did you have a question?
Yeah, what propositions again?
Okay, logical propositions are the formulae that we talked about in this morning's lecture. All right, so, and we're interested in the logically distinct ones, the ones that are quite, no two are equivalent. Okay, well, gosh, really? How do we know that? Well, think about it. We saw in this morning's lecture that you can define any particular logical operator, or indeed logical formula, over n different logical inputs by drawing up a truth table for it. And we saw in this morning's lecture that there will be 2 to the n, that's this exponent, rows in that truth table. There are that many different possible combinations of input values. So if you think about it, when we're going to define a proposition, we draw up 2 to the n rows, and for each of those rows, the output can only be either true or false. So we're back to this idea. There are 2 to the n outputs we've got to fill in or define, and for each of those, there are 2 possibilities. So we get 2 to the power, 2 to the n, logically distinct propositions. And that's one proof or one way of understanding why that is the number of different ways we could fill in the results column on our truth table. Well, an immediate corollary, if you're not familiar with the word, a corollary means something that follows pretty much for free from something we've just seen. So if we have a proof, we said, gosh, well, if that's true, well, it's easy to see this pretty much straight away. So as a corollary, the operators that we talked about this morning, and or, well, those are particular logic forms of logical proposition. And if we just think about P and Q or something like that, there's just two variables involved to define the basic operators themselves. So how many different ways could we have defined a basic logical operator with two inputs? Well, just plug in the number 2 here. We get the rather nice little expression, 2 to the 2 to the 2. Okay? And if we work that out, that's 2 to the power 4, which is 16. So actually, there are 16 different logical operations over two input variables. So now you're perhaps feeling rather frightened and thinking, oh no. So just when I thought I knew about logic already, and I know about and I know about or, and you know, that's probably the heart of it, now you're going to tell me I have to learn 14 more different squiggles. Actually, no. So we could do that, and indeed, for example, something that one of you pointed out this morning, if we felt a bit sad not to have exclusive or, we could introduce it, we could give it a name. I haven't been very imaginative about that here, and there it is. It's just like the or we saw this morning, except in this case, it has a false in the result column for the last row. That's the only difference. But do we need to do that? And connected with that, is there some particular reason why we started with and, or, and not? So here's another little theorem. The fact is that the three connectives we already saw in this morning's lecture, and, or, and not, they are enough. Now let's be careful about that, come back to that, where they're enough to express the logical equivalence of all others. So anything that we want to say logically, there will be a way of saying it only in this propositional logic world. Okay, we don't need 14 other different operators. It will be possible to express a logical equivalent of anything we want to say that uses only and, or, and not. So that is, it is in that sense that it is possible that I'm using the word enough. It may be that there will be some cases, indeed it is the case, that there are some operators where if we instead tried to write down the equivalent in terms of and or not only, what we need to say turns into a much bigger formula. And if we have other operators, they're convenient, they're helpful, they allow us to say some things much more briefly. And that's important, and we shouldn't overlook that. So we do sometimes want to make use of other operators, but it's a key thing for you to know that we can always turn them into equivalents that only use and or not. And that's useful for you to know because that means you've got a way of conquering any other kind of funny squiggles. At least one tactic is to say, hang on a minute, this is confusing me. Let's turn this into an and or not formula. I understand those, and then you can use those algebraic laws we saw this morning and everything else. So that's a very important thing for you to know. Well, I'm asserting that this is the case, that and or not are enough in this sense. How do I know that's the case? Well, one way to make good on justifying that claim is to think about the propositions in at least the two-variable case and just go through blow by blow. Say, okay, here we go. I've got 14 operators to go. Here's the first one. Let's take XOR again that we've already seen. and say, all right, so it's notice the point I was making a moment ago. Of course, it's much shorter just to say P, X, or Q. But it is possible to say it without exclusive OR. Here's one way to do it, perhaps a fairly easy and natural way to understand. We want to rule out, it's like the inclusive OR, P or Q, but in addition, we want to rule out the case where both P and Q are true. So we're saying, well, P or Q, the inclusive OR that we had this morning, must be true, and there's something else we require. We do not want both P and Q to be true. So if all that is the case, that is equivalent to P exclusive OR Q that we saw defined in its own table a moment ago. So what you could do is you could, as I say, go ahead and, for example, work your way through another 13 operators, and that's actually quite an instructive exercise. You could do that, would do you no harm at all. Sometimes I vary these questions a bit just to keep you on your toes and because I think of a slightly more interesting question, and this is one of these cases. Rather than the rather blow-by-blow proof, we say, well, here's this one, and here's this one, and here's this one, and oh, have I done them all yet? Oh, no, I haven't. Here's another one. That's not sort of perhaps deeply satisfying. So instead, let me ask you this question. If I give you a truth table, and I can fill in the final column any way I like, and what's more, the truth table could actually have any number of different input variables, can you come up with a method that looks at the truth table and says, I can write down a formula for that using only and, or, and not, in addition, of course, to the input variables. Do you understand the question? So this is for you to discuss with your neighbor. Some of you might even know such a method. Others you might not even have thought of it. That's fine. So that's the thing I want you to discuss. If you're looking at a truth table, for example, it might be this one, but it could be any truth table. Can you actually come up with a method for just reading off from the truth table? I can express that as an and or not formula. Go, discuss. I note I've got a hand waved up the back there. I'll pick up your question once we finish this discussion. Okay. Okay, we'll hold it there. Some people still talking about it, others perhaps have sort of thought about it as much as they want to for the moment. Now this is one of these questions. It's not a kind of short answer. The answer is yes or no, or use an and or something like that. It's a bit more complicated than that, so it's not the kind of thing where it's terribly helpful for me to ask people, okay, what's your method? Because it's a bit hard to sort of speak a whole method in one short answer. So on this occasion, I won't do it that way. I'll just show you a couple of examples of possible methods. So here's a possible method. You want to express when does this truth table give the answer true? That's what we're trying to do. We're trying to write that down as a logical formula. Well, one rather obvious way into it is to say, well, and we'll stick with the, we appreciate XOR is just an example. We could do this for any truth table at all. We could say, well, this, at the first cut, this truth table is going to give the result true when the inputs are such that we choose one of the columns with a true result. Okay, that seems reasonable, doesn't it? So we could say, when we get this being true is exactly when we're in one of these two rows. So if we're in this row, or, notice the word, we're in this row, then we'll get true out of this table, otherwise we won't. Well, I said we're in this row. That's a bit vague, that's not very mathematical. When are we in a row? Well, of course, it depends on the values of our logical input variables, P and Q. So we're in this second row when P is not the case, it is false, and, note the word, Q is the case. So I've now used all three words, or, and not, and perhaps you can see how I can now read off from the table one formula. So the whole formula is we're in this row, or we're in that row. There it is, there's that or. And this first part says we're in the second row, okay? P is false, it's not the case that P is true, and Q is true, and Q. So that's saying the inputs are such that we use the second row, or the inputs are such that we use the third row, okay? I hope that's clear. And in that, using that same method, you could perhaps do that for any truth table. Now, feel free to criticize my method as harshly as you wish. Does anybody see any problem or drawback with my method? I'm thick-skinned. Fire away. Bring on the flames. Right, yes? Yes. Okay, you're saying, well, you've insisted that this is the second row and this is the third row. Okay, recalling our terminology from this morning, or is commutative, it actually doesn't matter which way round I write them. So I would say, that's true. So I mean, if you find it easier to just read off the rows in some other order, go from the bottom of the table upwards, that won't matter, that my method will still work. So I don't see that as a big problem. It would give you a slightly different looking formula, but it would be logically equivalent. It would be the same size, it would be the same pieces, but in a slightly different order. So thank you, you're right in your observation, but I don't think that's a big disadvantage of the method. Now then, we've got another comment over here, yes?
As the number of variables that you're working with increases, the amount of time you'll have to spend working this out will also increase.
Okay, to some extent that's inevitable. You only said it will increase, and obviously if the problem is bigger, the work is bigger. And the question is, by how much will it increase? You're absolutely right, absolutely right. So, as I said a moment ago, when we say and or and not are strictly enough, I was careful to point out, of course the formula might get quite big. And you're saying, yeah, well, you've told us about exponential. You know, I mean, that could be exponentially many rows and so on. Yes, that's true, though I would say any method that insists that I can only get an and or not formula in the end is going to have some blow-up cases, because that's in the nature of things. Unless you're very careful, perhaps you could hybridize things or whatever. Any other criticisms or observations? Yes? Yes, I like that idea. Let's plug back in something we already know. For instance, just simple OR. If it was a really great method, you'd hope you'd just come out with OR, because we know that's enough. And you're saying, I can see that we wouldn't just get that. We'd get some non-complex formula. Okay, you're onto something there, and why is that? What is it about OR in particular? What's a general issue for my method? Hint, I'm saying, now take all the rows that give you a true result. This could be, as our colleague has pointed out, could be quite a big table. Yes?
With the first OR, you have a lot more true.
Okay, there are more trues than falses. So in some tables, it might be almost all trues. So I'm setting myself up for a big formula because I've got to have a piece of formula for every single true row. And, of course, if none of them were true, I would be stuck because my method starts, pick all the true rows, and there aren't any. So I can't write anything down. Well, that's a bit of a special case, but on the other hand, it is a whole. So for both of those reasons, I might like an alternative method, the opposite method, if you like, where, perhaps a little oddly, I start by saying, well, let's focus on the true columns, but let's focus on the false ones. And you might think, well, that's a strange thing to do. I mean, it's going to be false. In those cases, you'll get the wrong answer. Well, yeah, but I've got a little operator called not. So that's not too hard to fix, is it? Right? So the idea behind this method is, well, when will this table, it's the same table, but looked at a different way, I'm concentrating on the false ones, when will this table give me a true result? When we are not using this row, and, note the word, we are not using this row, then we will get a true result. So it's a similar idea. This time the whole formula comes out as an and this first bit means somewhat unwieldily that we are not using the first row, and this one means we are not using the last row, and again we describe the rows by just, well, P is not true, Q is not true, right? So this is the first row. P is not true, and Q is not true. And if we're not using that first row, and we're not using the last one, then we get the true result. So these two methods, combined in some way, I think should convince you, yeah, we can always do this. We can extract an and or not formula, albeit, as some of our colleagues have very rightly pointed out, sometimes we'll get quite a big formula. You may know other methods. You may be able to invent other methods. So we've seen then that just and or and not are enough in this guarded way that we've defined that. Okay, so these three are enough. So we've said we don't strictly need more. Okay, we don't need more. Could we have done with any less? Well, actually, if you think about it, there is a corollary. Remember, one of those little, oh, but that means this as well. The corollary, actually, we don't even need 3. We only need 2. And why is that? Because and or are tightly connected with each other. Each one is just a mirror of the other one. So because of that, we can get away with, if I put it that way, just not and one of or and and. If we don't have an or, we can make one, I may put it that way, because it's logically equivalent to a negated and where we negate the inputs. That's the mirror property. Okay? Put it in the mirror. Equally, if we didn't have an and, we can always make the logical equivalent of that by an or of the negated inputs and then negate the result. So actually, we only need 2 connectives. Well, I feel we would be wholly lacking in ambition if having seen that 3 logical operators are enough, and then having improved it to 2, we just stopped? That doesn't seem very ambitious, does it? Maybe we only need 1. And indeed, that turns out to be true. So if we, at the moment, we've got to the position where we know that it would be okay to have a not and just an and, that would be all right, or we could have a not and just an or. Those just one of those collections of just 2 operators we've seen would be enough. So we're pushing things a little further here. We are, if you like, taking a not and an or, and we're sort of pre-assembling them. So the only way you can have a not and an or is in this sort of pre-assembled, you take the or of 2 things and then you negate it. That's it. You can't have sort of free-floating nots and ors sort of put together any way you want. A couple of ors over here with no negations in sight, and then, you know, lots more negation. No, no, no. Every time, you always get just a negated or. Or, alternatively, another single operator, a negated and. So it's similar to what we had before, but it's a very limited configuration. It's the idea of a not with an and or a not with an or, but they're kind of pre-assembled in this very tight way. And perhaps your first thought, unless you happen already to know this stuff, is, well, that's just going to be too restrictive. We can't be doing with that. You know, surely there'll be some things that are now just impossible to write anymore. No, turns out not. We really can get away with just 1 logical connective, if we wish to. So how would we prove that? Well, we certainly don't want to go back to reading off a complete general method or coming up with a recipe for 14 other connectives. We don't need to do that. We've already seen that. So long as we can make a not and an or, we've got enough. Or alternatively, if we can just make a not and an and, that would be enough. So that's all we need to show. If we can just show that, everything else would follow. So here we go. Suppose all I had in my kit bag was a negated and. By the way, in case you haven't picked up on it, the idea of this upgoing arrow is it looks like an and, this sort of inverted V thing, but then with a vertical bar through it, so it's sort of negated. Okay, that's the mnemonic. Anyway, a negated and. Suppose that's all I've got. Will that really be enough? Yes. Suppose I want to have a not. So how can I write not? I can't even write a simple thing like not. Yes, you can. P, negated and P. That is to say, not P and P. We saw this morning that P and P is just P itself, so not P and P is just not P. So we can, if we've got negated and, we've got enough to build a not. Oh, but what about or? That's going to be more tricky. Well, actually, it isn't, because of the nice mirror property. We've got a negated and. We're halfway to an or already. All we need to do is to negate the inputs as well as the output, and we've got an or. So if I've got, for instance, negated and, here's how I can make a not, here's how I can make an or. You might say, oh, but you've cheated. Look, you haven't just used negated and here, you've used not. Well, yeah, I'm just sparing you a long-winded formula. I've just told you how to write a not as a negated and, so you can make the expansion for yourself. So that's enough as a proof. I emphasize again, and try a few and then you'll believe me, if you actually do this, you may get big formulae and slightly strange-looking ones, where the whole thing's full of these variables again and this one operator that you just use into oblivion. So it's weird kind of stuff. So is it only abstract mathsy? Who knows? Maybe some surface physicist will come up with some strange new computing medium, and they'll tell the world, You won't believe how fast this is. Just leaves everything else completely behind. The only problem is it's very limited. We haven't been able to build many gates yet. You say, oh, what gates can you build? Could you build a negated OR, for example? Oh yeah, we can do those. Who knows? Who knows? There have been some very radical machine designs based on very new sort of basis for architecture. Okay. Time for you to have a break from me. I'm sure you'll agree. Well, okay, I cheated. I only gave you half the proof. I showed you that a negated AND was enough. Discuss. What about negated OR? What happens with that? Okay, natural lull, I'll jump in. So in a word, what can we do? We can reflect, put it in the mirror. It's the answer of the moment. What? Some of you may be saying, what? Put it in the mirror? What are you on about? Well, above the mirror line is the proof I gave you a moment ago for the negated AND. Put it in the mirror, the up arrows become down arrows, the OR becomes an and so on, and you've got the corresponding proof for the negated OR. You begin to see what I mean about this mirror stuff. It's not just cute, it saves us a lot of work. It's great, 2 for the price of 1. Okay, so that's the first and larger part of the lecture, talking about, so how many connectives do we really need, and some investigation of that in both directions. I now want to spend the rest of the lecture talking about a particular connective, which, given what we've said, although and or and not, would be strictly enough. They're not necessarily the most convenient or the clearest or the shortest way of writing everything. It is sometimes useful to use other operators. And one that crops up quite a lot is logical implication. And indeed, that very phrase goes with sort of everyday use. You know, in discussion, somebody might say, yeah, but hang on a minute. The logical implication behind what you're saying is this. Or logically, surely that implies, and so on. So this whole idea of sort of logical reasoning and the idea that one thing implies another goes to the core of how we normally use the term logic and logical reasoning. And there is indeed an operator for logical implication. And here we begin to part company. If you're also tracking the very beginnings of computer architecture, you've probably got, you know, AND gates and OR gates, and indeed NAND gates and NOR gates, and so on. I'll be very surprised if you're designing using implication gates. As far as I know, the hardware people don't do that. But on the mathematics side, logical implication is very important to us. And it's not utterly different stuff. It's just another operator, at least in the terms that I'm presenting it here. So this is one way of looking at logical implication. So it's a connective. It has two logical inputs, everything much as we've seen before. It has its own squiggle. Okay, it's an arrow. Some authors will write it as a single-shafted arrow, some as a two-shafted arrow. I've gone for the double one, which is quite a common choice. Don't be put off by that if you see single arrow in a textbook you're using or whatever. That's fine. If it's logical implication, it's this thing. So, if we want to know what it is, here it is. We know that it's enough to give you a truth table, and that completely pins it down. And no, it's not OR, it's not AND, it's not exclusive OR. It's a new thing we haven't seen before. We know, however, that whatever it is, it must have an AND or not equivalent, because everything does. Indeed, it's got lots of them. The simplest one is this. So P implies Q is not P or Q. And the informal reading is, just nudge that up. The informal reading, it's always useful, and OR have natural informal readings. Implies is perhaps not so much a word. We do use it a bit in everyday speech, but not nearly as much as and OR. So we can read it, if P, then Q. Or P guarantees Q. Or P is sufficient, or it's enough. If we know P is true, then we know Q is true. Now there's a gotcha, a trap, a thing that it's easy to misunderstand. So let's pin it down, identify it, and hopefully resolve it for you. When people are introduced to the truth table for implies, and they remember to think of it as if P, then Q. Okay, here we go. Let's check then that this truth table makes sense. So let's take the easy ones, the ones at the very top and the bottom. So it says if P, then Q. Well, P is false here, and sure enough, Q is false as well. So, yeah, that follows the rule. If P, then Q is true in this case, because P was false. It didn't hold, so we didn't expect Q to be true either. On the other hand, the one down at the bottom of the table is equally straightforward. It says, if P, then Q. We look, we say, well, in this case, P is true. Oh, if P is true, then Q would better be, oh, yes, Q is true as well. Yep, so the implication is true here as well. So far, so good. And then we've come to this third row, and we say, okay, if P, then Q, and we look at P, and we say, well, in this case, yes, P is true, so if P, then Q, oh, dear, oh, Q, no, Q is not the case. Well, that's bad. It's not, the implication doesn't hold then. If P, then Q fails in this case, right? So it's false in this case. All fine so far. And most people are perfectly happy up to that point. The one that really upsets people, as it were, is the second row. And you say, if P, then Q. We come along, we say, if P, well, P here is false. Oh, okay, P is false. Well, okay, so we're not holding out much hopes for Q then. And then we say, blow me down, Q is true. Well, that's funny. I thought you said it was if P was true that Q is true. And here it is just being true anyway. And I want to say the implication is true. And you are feeling sort of darkly murmuring about it. Okay, here's an example. I think the problem behind this is that people want to read the arrow as kind of causes. It's because P is true. It's the fact that P is true that then leads to or causes Q being true, okay? And that is a pitfall. There are forms of implication that are like that, but implication itself does not mean or point to or guarantee there's a causal relation. If this is true, that's true. And if it isn't, well, then this can't be. No, it's not saying that. A better reading is, well, if P is true, then Q must be, all right? Or P guarantees Q. Here's a little example that does it for some people. In fact, generally, over the while talking about this, a lot of people have said to me that finally this is what made it click for them. Let's remember your generous rich aunt, who may or may not be fictitious. And suppose that your generous rich aunt, uncle, or any other relative you can encourage to take an interest in mathematics has indeed given you all these exciting books, and you resolve in your mind that when you finally graduate, you really ought to give them some little gift in return. And you decide that this little gift for your rich aunt could appropriately be, thinking of your rich aunt and all that she likes, a silver vase. You might think, gosh, you overestimate my bank balance. Okay, well, a small silver, a miniature silver vase. Okay. There is just one thing that stands in the way of your excellent plan, and that is, you know absolutely nothing about silver vases. Nor do I. Well, almost nothing. I can tell you one thing, and that is, when objects are solid silver, you can send them to a special assaying office, and they will test it in a lab. Say, is this really silver? And if it really is silver, they will put a hallmark usually on the base of it, and they will stamp it and say, tested and approved as solid silver on the base of the vase. Now you're saying, what on earth has this got to do with logical implication? Everything. The knowledge I have just given you amounts to a logical proposition. Hallmark implies silver. If it has a hallmark, then it's silver. Notice, stamping the hallmark on the base of the vase does not make it silver, okay? It's not causal. It's not magic. It's not alchemy. So the question you could also ask is, I've just given you this advice. Having a hallmark on the base is the guarantee that it will be silver. When would I have lied to you? Okay? Would I have lied to you if there was no hallmark and sure enough it's not silver? Clearly not. What I said was true. Would I have lied to you if there is a hallmark and it is silver? Clearly not. It's true. What if there is a hallmark and then, horrors, somehow it's a fraud and it's not silver? Then I would have failed you. But notice this, the problematic case. Suppose the object did not have a hallmark on its base, yet in fact it was solid silver. There's no problem with that. I mean, maybe somebody never bothered to send it off to the office, right? It's not having the stamp put on it that makes it silver. So there are silver objects out there in the world that have never been to the hallmarking office, so they've never had one. So my advice, the implication that I gave you, is still true. If all else fails, remember this little translation rule, which will keep you straight. Whoa, can't get my head around this implies. Remember, P implies Q is logically equivalent to just not P or Q. So it's not even a big translation, it's a nice simple one. So do notice this, that when P is false, that is to say, in my little example, there is no hallmark, then immediately we know P implies Q is true. We say it's vacuously true, right? The left-hand side is false. But now it doesn't matter what the value of Q is, whether or not the vase is silver, the implication is true. And that's the thing, I think, which gets people. Hope you find that useful. We'll get a chance to practice some more with implication in the problem classes this week. So we've got this little operator, implication, and as you might guess from the notation of the arrow, it has a way round. It's the thing on the left that implies the thing on the right. That's not at all the same as saying it the other way round. So we need to be careful. But for any implication, we do have some related implications. So if we've got an implication P implies Q, we can ask, how, if at all, does that relate to the converse? I'm sorry, more names, that's the way it is. These things have names. The converse implication is Q implies P. The inverse is not P implies not Q. And the contrapositive is, notice that we flip them around one side to the other. Q has gone to the left, P to the right. But we've also negated them. That's called the contrapositive. And the key thing to remember is that the original, P implies Q, is equivalent to the contrapositive. That can sometimes be a very useful way to prove things. I'm trying to prove that if P is true, then Q follows. Oh, that's hard. P is just so awkward to get a way into. Okay, turn it around. Show that if Q fails, P must have failed. So that's a very useful way to go. The converse-inverse thing is just the same thing again, but with the variables the other way round. So there are not really two rules here. As so often, there's really just one. It's just their simple variants of each other. So this is the thing to remember. The original and the contrapositive, you flip around left to right, but you also negate both left and right. Then you get an equivalence. Now at this point, we have the exciting introduction of some green technology. Green technology is in the news at the moment. It's all the rage. Chemists are up to it. Green technology. Material scientists, green technology. We mathematicians don't want to get left behind. So I give you green technology to conquer what might otherwise be a daunting little calculation, by which we shall show that it really is true that the contrapositive is equivalent to the original. Green technology, in the form of the ever-popular sliding window, allows us to reduce this to its constituent stages when we are no longer so fearful of it. So we just take it a step at a time. Here's the contrapositive. We know by the little translation rule I gave you, and implies is just not the left-hand side or the right-hand side. So in one step, we get not Q or not P. And then in another step, we've got a double negation on the left. Well, that's rather easy to take care of. Double negation cancels. And then we remember that OR commutes. Okay, so it doesn't matter which way round you put the left and right-hand side in an OR. So we can switch them around. We get not P or Q. Ah, there's that pattern again. That's the form of an implication. So by the translation rule being used backwards rather than forwards from the not and the or to the implies, we get P implies Q, which is what we wanted. And the green technology of the sliding window has done its job. As we draw to a close, as I must, sometimes I said that the left-hand side implies the right-hand side is not at all the same thing as the other way round. That's asserting something different. But sometimes you do get both holding. When you have both P implies Q and Q implies P, that is to say they're locked together. If one's true, the other is true, and the other way round. So it's kind of the equals operator of logic. You see that? It's when you've got false and false, you get true. When you get true and true, you get true. But if the inputs are not equal in value, then you get false. So this is a double implication, and we can express it Q implies P and P implies Q. So it holds both ways round. So occasionally that symbol will be useful, and again notice it's shorter to write this than it is to write that. But that's all it is, shorthand. So for this thing, we can, the double implication, as I say, you can think of it as the logical equality operator. Sometimes it's read if and only if Q. P is both necessary and sufficient for Q. A very small example as we draw towards a close. This is our last example, then we'll summarize and finish. So here's a little example of two things that are locked together in this way logically. So P is the assertion, we're introducing numbers just for a change, Okay, so suppose we've got a number x here. X squared is odd. And there's another logical assertion Q, which says not x squared is odd, but x itself is odd. Well, with a bit of thought, you will, I hope, agree with me that, well, hang on a minute, if x is odd, then x times x will be odd. And for that matter, if I know x times x is odd, x must be odd. So it works both ways round. Indeed, so it would be correct then to say P if and only if Q is true. X squared is odd if and only if x is odd. And if we unpacked it using the translation rule I gave you a moment ago, we could see it like this. You'll get a chance to practice using